Hello friends, welcome. Now friends, in this world of AI, we suddenly have a new announcement in the tech world, which is Microsoft Marijuana One Chip carves a new path of quantum computing, and the whole world is going crazy because of this announcement, though quantum computer as a subject is being discussed for so many years now. Okay. Now friends, in this video, we are going to deep dive a little bit so as to get the nuances out so that people can intuitively understand what the concept is and why this announcement is so important. That's all we are going to discuss in this video, right? And just to basically make an opening announcement, I am not a quantum computer expert, but since I am an engineer, I have an understanding about quantum computer as a subject, right? To an extent that whatever I have studied in my days when I was in engineering, I am leveraging that subject understanding to able to appreciate the importance of this announcement, and whatever I have learned, I am going to convey to my viewers so that they can leverage the understanding that I have been able to generate. Okay, so let's go step by step. The first is that what is quantum particle, right? And how they are different from classical particle. That is what we are going to understand first, and which will make us understand how quantum particle works. Now, classical particles are big, particles. Like for example, the human body, which is an aggregation of quantum particles, can be considered as a big entity which behaves in a classical way. What does it mean? Now, if you are sitting, let's say if I am sitting here in front of the computer, nobody can tell me that I am 100 meters away from my location. My location is deterministic. My properties are deterministic. Whereas in case of quantum particle, which is actually at the level of atom or maybe electron, which is very small, they are non-deterministic in nature. So their location cannot be specifically pointed out in space. You don't know where the quantum particle is. You can't measure them accurately. There will be always a level of uncertainty. And that is determined by the distribution function of the particle rather than the accuracy of the location of the particle. Means there is a probability distribution which determines what probability is the highest to find that particle in that particular location, what probability is the highest to find that particle with a particular energy state. That is, in simple terms, quantum particle is all about, right? So let's understand this a little bit more deeper. Let's say I have a quantum particle here. Maybe this is an electron. Now everybody knows the electron has got a spin. Right? The spin can be either 1 or 0. So I am representing that spin as 1 and 0 as two states. Now, since we really don't know how much of this spin is biased towards 1, how much of this spin is biased towards 0, that is what we call as uncertainty. We don't know. But there could be a mechanism to either bias this spin more closer to 1. Like if you see this arrow, this is an arrow in 3-dimensional space. This is a vector. So you can tune the vector closer to 1 than to 0. So when you make measurement of the spin of this particle, then you will be likely getting the result as 1 compared to 0. That is where the measurement bias is all about. So when you're making a measurement, this is a probability distribution. When you're making the measurement, the bias would be towards 1 because this dial is more biased towards 1. Now, if the dial was biased towards 0, then the probability of 0 coming out higher is going to be more. But the point here is that to understand, as soon as the measurement is done, then the indeterministic nature of the quantum particle is lost. This is the very peculiar part. Means there could be multiple such quantum states which may exist in space, but everything will get unfolded into a deterministic state as soon as you are making the measurement, which is very peculiar. It never happens in case of a classical thing. In quantum thing, that measurements will destroy all other states which exist simultaneously along with the current state which you have measured. Okay. So here you will find that this single quantum particle, which can be in two states, either 1 or 0, just like a bit can be in 1 and 0, right? The 70% probability of it being 1 is higher because the dial is actually pointing towards 1 or closer towards 1 than 0, and the 0 can be of 30% probability. So this is how a simple quantum bit right, is represented, it is based on probability. For example, here if you see 1 and 0 are both of equal probability because this dial is pointing parallel to the x-axis, right? So what we are basically trying to say, the state of quantum particle is not deterministic but probability distribution. Now how the probability distribution looks like, let's understand this. Again, we are in a single quantum particle which is 1 or 0. Now this single quantum particle 1 and 0 follows a equation which is called Schrodinger equation. Now this Schrodinger equation, if you see, when you plot the Schrodinger equation, it's a distribution function, and we are not going to get into the equation. I'm just plotted it to show you that this follows a distribution, right? You see, it follows a distribution like this, and you will see that the state which is at the bottom 0, right, which is the energy state, is more likely because the dial is pointing towards, more biased towards 0 than towards 1. Therefore, if you make a measurement on this particle, the quantum particle, you are likely to get the state as 0 compared to 1. Okay, that's all. Now let's go to the real concept here. Now, how quantum computers work? Because quantum computer cannot work with one single quantum particle. It has to be multiple quantum particles together, all working together in the mode of entanglement. So I have shown here 3 particles in the state of entanglement. Now what is entanglement? Entanglement is again a quantum behavior. It basically, to make you understand it intuitively, because it is again a very, very difficult concept to understand, the intuitively it basically means that all these independent quantum particles interact with each other to work as if that they are one particle. That's all. That is simple as entanglement is there. So if, let's say, if you have a quantum computer with 3 bits, it can be 7 bit, 8 bit, 10 bit, 100 bits, 120 bits, 1000 bits, right? So all these are individual bits. When you call a quantum computer with 1000 bits, then what happens is that the state of that quantum system using 1000 bits are working in collaboration with each other in a process called entanglement, so that the whole behavior of the system appears as if that they are one single entity, not individual entities. Okay, got it? Not individual, they are single entity. Now what does it basically mean? Let's understand this. What is basically mean when you say it is a single entity? It means that the integrated distribution function which I showed you for a single quantum particle here, this is a distribution function which is the Schrodinger equation. The integrated distribution function will look something like this. It will have 8 peaks. Why it will have 8 peaks? Because this is a 3-bit quantum system. And there will be 8 states which are going to be available with different probability distribution or probability of occurrence, right? So this is the probability distribution of different states, different peaks and troughs. Like this is 1 peak, this is 2nd peak, this is 3rd peak, this is 4th peak, this is 5th peak, 6th peak, 7th peak and 8th peak, right? So there are different, states here. Every states can be given a certain number. Like classical system, 3-bit system, it starts from 000, then we have got 001, then we have got 010, then you have got 010. Similarly, you can label these states as 000, like that. But the difference is that each and every state has got a different probability distribution, or the likelihood of that state getting measured at the time when you are measuring this system, right? Because you have to measure this system to see what the results are. So that is going to be measuring this state. 000 will have a different probability, 001 will have a different probability, 010 will have a different probability. It all depends upon the distribution function which emanates out of the interaction of all these 3 particles together, these quantum bits together. So their distribution and how these dials are biased by the gate functions which you are going to use to bias them. So you can bias them, based on the system that you're going to use for biasing them. So if you bias one of them, then the distribution function will change. Now, quantum system, just because they have this entanglement capability, right? Entangling this whole thing together cannot function, independently, because a quantum computer without a quantum algorithm is useless. you need to figure out an algorithm which will give you this result of 43%, which is the state 101, which is going to be the solution of this problem. Because as I told you, as soon as this state is measured, 100 is measured, all other states are going to get lost. At the time of the measurement, everything will get lost. Nothing you will be able to unlock after having made the measurement. Therefore, quantum algorithm ensures that the state with maximum probability gets amplified through the process called constructive interference, and the states when measured, only when you measure that, only this state shows up. So that's the whole purpose of quantum. When you are trying to solve a problem using a quantum algorithm, then what happens is that the processing will happen simultaneously for all the states, but the only solution to that particular problem, because you are solving the problem, because as you saw in solving classical computers, you keep iterating, and the solution comes out. Similarly, in quantum computer, instead of sequentially feeding the solution, it is all parallel, fed together, and you get all the states, all the solutions, but the answer to that problem will get amplified because the algorithm is set such that this is going to show up, and when you measure that, this is going to be the solution to the problem. Okay, so that's how the quantum computer works. Without an algorithm, the quantum computer makes no sense. Okay, now let's come to the main issue, why this announcement is so important. Then we are going to go into the little bit of application part. Now, this announcement is very, very important is because of this fact, and I'm not going to go into the technicalities of this detail, what particle that they've used, and I'm going to keep it at a very high level. Now, these individual quantum particles that you see here, which is entangled together to create a larger system, which works in unison to create this wave font, is very, very susceptible to noise. Means, if there is an external noise, which can create an impact on this state of this quantum particle and disturb the state in such a way that this whole entanglement loses relevance based on the algorithm that you are going to use. But those algorithms are not going to give you the expected result. So you have to manage noise, or you have to correct errors. So major work on quantum computer is to deal with this noise, which is going to disturb this state of these particles arbitrarily. There will be external biases which are going to come up because of some radiation, some light, some volcano, or not volcano, so earthquake, some slight undulation of the building, or maybe some voices out there. So these are going to get disturbed, and that is why, in order to mitigate the noise, this whole system that you see here, which is being pointed, it cannot work in an open environment. Just like a PC, it has to be encapsulated in a heatsink, right? In order to cool it, this has to be cooled in using a supercooled solution so that the noise can be mitigated. Now, I think still now we have not been able to appreciate why Microsoft's Majorana One Chip is leading to a path of scalable quantum computing. Why this is so important compared to the other announcement, though the number of bits that they are using is much higher than this computer, which just works on 8 bits. It is because of the fact that they have created a topological framework. Again, this is a technical term, and we are not going to understand what topological framework is, because there is no point. There are other experts which are going to do a better job. What I am going to tell you is that these particles, which are supposed to entangle with each other to work in unison to give you this wavefront, these particles are set up such a manner that they become less susceptible to noise. That's all. So you can create a system which ideally would be more susceptible to noise, but if you use the concept which Microsoft has come out with in the Majorana chip, which is called a topological framework of creating quantum bits, then this bit is going to be less susceptible to noise. Now, since this is going to be less susceptible to noise, which basically means that you can create a system of large number of bits, because the basic challenge in increasing the number of bits in a quantum computer is that it becomes too susceptible to noise, because more the number of bits, more the system will become biased because of external noise. So if you can make these particles, right, stand on their own without getting interfered with noise, then you can scale this whole system up to 1,000,000 bits, which is required to break problems, real life problems. And I am going to go into a little bit of deep dive to make you understand what kind of real life problems that are going to get solved. Now you probably understand that what is the importance of this. Why this is getting amplified? It is only because of this that these particles will get set in such a way that they will be less susceptible to noise compared to a conventional quantum computer, which are more susceptible to noise, and therefore very difficult to manage large number of quantum bits which are required to solve real life problems. Now friends, what I did was I actually had written an article long back regarding the solutions to one of the major problem of encryption, right? So what I have in this article, I can paste the link of this article. This is basically explaining Shor's algorithm, right? Now, I'm not going to go into the details of Shor algorithm because this is very, very complex. Sometimes I also get confused when I read this article again. I forget what I've written earlier. But to give you a sense, what does it mean? Let's start with this. Let's say I told you that you have a quantum system where you are feeding input. Let's say 2-bit input. Then the outputs are going to be in the solution to that 2-bit input, which is an fx. Fx means you are having a function x running, operating on these 2 bits. So there will be f0, f1, f2, f3 because there are 2 bits, so all possible combination. So these outputs are emanating simultaneously, and as I told you, that the solution to the problem will be set such a way, the algorithm will be set such a way that one of the solutions will be amplified and rest are going to be destructively interfered with, so that their probability becomes very, very minimal. So there will be a peak here. Let's say f3 is the solution. Now what Shor algorithm is doing, in simple terms, again we will not get into the details. So you have got a number k, right, which is a very, very large number, right? And this number k is made up of 2 different prime numbers, and you have to factor it. Using a conventional computer, you can't solve this problem, right, in a short window of time if this number is very, very large. So what quantum computer is able to do is, again, we are not going to get into the maths here. It's all written here. If you want to read it, you can basically read it because it is going to get too confusing and you will lose the essence of this video. What I am trying to tell you is that how this whole system works, and to give you an intuitive understanding of this, is that it converts the problem, which is to find out the factor of k, into a series, a number series, right, which is repeating, with a period r. Because if you are able to create a number series which is repeating in a period r, then you can basically deal with this concept. When you feed million bits, then you will get some kind of combination of output, which is 2 to the power some million, right? A million. And those are going to be simultaneously processed using this quantum computer. And you can set up the system in such a way that whatever is your answer will get amplified. So what you are doing is you are basically converting. The Shor algorithm does what? It converts the problem into a series. That's all. And that series is fed into the quantum system. And the algorithm is set such a way that one of the results, which is the result of the solution to the problem, gets amplified. That's all it does. And therefore, you are able to break the encryption. And I'm basically describing some mathematical concept like Fourier transform, etc. Again, you don't have to get into that. Don't get overwhelmed by this. So this is the essence of the concept of quantum computer. And this is why the Microsoft Majorana chip is being discussed worldwide, because people have now got confidence that because of the fact that you are able to stabilize this quantum particle so that they become very, very less prone to noise, you will be able to scale up the number of bits to a magnitude of 1 million, which is required to solve this problem which I just described, the Shor's algorithm. To break the encryption, which is the Shor algorithm, right? So that is what I wanted to discuss, friends, here. I don't want to go further on this, otherwise I'll get exposed myself because I have no understanding about the subject. But when I was researching this topic, I got a sense as to why this is important. And that is what I wanted to talk to you in this video, to make you understand the essence of this announcement and why people are getting excited, because this is just an 8-bit computer today. It is not more than, there are computers which multiple, 1,000 bits also, but those computers cannot work efficiently because those 1,000 bits will require a lot of bits to be consumed for error correction, right? So thanks friends for your time. I hope that you like this video. This video coming from me, who is not an expert, may surprise you, or maybe people may not take it seriously. That's fine. I was trying to learn myself, and in the process I thought to get my understanding to the viewers also, if that may be useful to you. And if you find that it is too trivial, that's fine with me also, because my intent is not to become a quantum computer expert, but to appreciate this announcement. That's all I was focused on. Okay friends, thank you very much for your time. I'll come back with a new video next time. Thank you very much.